Okay, ladies and gentlemen, today we are going to talk about the cables. Our subject is today cables. Yes, where we use these cables is you well know here, for example, if we have a suspended bridge like the phosphorus bridge, we use cables. So here there is a bridge deck over here, and all the deck load is transferred to the main cable with these vertical secondary cables. So our main cable carry all the load. Or what we can do, we can use a cable car system. For example, let's say we have these supports. In these two supports, we have cables, and there is a cable car moves between 2 points. These 2 points, people stay here, and it slides from one point to another. This is another point to use the cables. So we have many applications for the cables. Today we are going to talk about the how we can calculate the internal forces in the cables. Okay, in the first session, I'm going to explain how to calculate it. In the second session, I'm going to solve a few examples regarding this issue. Actually, cables are an easy subject. You can easily handle it. So you can do it easily. There are a few small rules you have to know. If you apply these rules to cables, it's easy, really easy when we compare with the other subjects in this course. This is really easy. I know you can do it. So at the end of the day, we are going to ask a question for cables in the final exam. So this is really easy. Please catch this question in the exam. So there are some rules for the cables. Okay. Key points. The first one is, the cables are bendable. It's like for example, this is a cable for my computer device. This is a bendable. We can give any shape to this cable. It's easy. So they can't carry any bending moment because they are bendable. They don't have any stiffness, any resistance for bending moment. So cables do not carry any bending moment. Okay, they don't carry any bending moment. What they do, they only cables carry only tension load. Okay, they carry only tension load. On this cable, there will be a tension. Okay, it changes its magnitude from one location to other one, but the logic is that there is only tension load on the cables. And the other one, when we compare the load that the cable carry, for example, here, where, here on the bridge, this is our cable. It has an own weight. That's okay. It has a self weight. Under the gravity laws, But when we compare the self weight with the other live loads that we carry, for example, we carry with this cable the load coming from this deck, bridge deck. So what we have on this bridge deck, okay, self weight of this bridge. Also, we have cars, people, everything on this deck. So the cable here between two pylons carry all this load. So when we compare this live load with the self weight of the cable, self weight is really, really small when we compare with the live load we carry. So in our calculations, self weight is nothing for our results. That's why we can cancel it in our calculation, and we can ignore it. Okay. Let me write it here. Self weight, of cables are ignored when compared to live loads carried by the cable. Okay, so what we have here, there is no bending moment on the cables. There is only tension load, and we always ignore the self weight of the cables in our calculations. Okay, this is our key points. These are our assumptions at the beginning to do our calculations. Okay, let's do the first cables under the point loads. Second page. So I'm gonna go sketch for you. The tables under point load. Perfect. Now, Okay, that's better. Here we have a support on A, and here we have another support. A here, I have one point here, another point here, another point. So there is a level differences between the supports. This distance is this differences. Oh, let's say only that's better. Okay. This is point P1, P2, here is P3. Okay, at these C points, we have point loads. Okay. P1, P2, P3. Okay. If the distance between support span is L, and if we change color, the distance of this point load from the point A is x1, here is x2, x3. Okay, this is our system. So we have a cable. Basically, what we have here. Imagine you have a cable and you apply point loads. You apply a point load to this number. So you have a cable like this. When you apply a point load to midpoint, for example, you're gonna get a shape like this. So the cable portion at the left-hand side and the right-hand side will be like a straight member under this point load. So if we increase the number of the point loads on the cable, as you can see here, for example, if I apply here and apply here, what I'm gonna get, I will have a shape like this. So in between these point loads, the cable will be like a straight member. So in this example here at the left-hand side sketch, I've drawn with the black here. You can see there are 3 point loads. So the cable acts like a straight member. It gets a shape. It's a straight shape actually. So it's a cable. The behavior is not changed. Like, okay, it's gonna only carry tension load. That's okay, but its shape is like a straight member. So in between these loads. So this is an important point to make calculations. I'm gonna clear this part. Here I have another. What I have, for example, I know the point of rotation of this point in the vertical direction. If we draw the free body diagram for this shape, free body diagram. Okay, remember what was the free body diagram? We learned free body diagram in the first session, I guess. What was it? We draw a sketch and we draw all the external loads and possible support reactions on the sketch. And then we try to understand what we have. Okay, what we have and what we are gonna solve. So let's do it for this part. Okay, again, I have this one, and then I have something like this, and then something like this, and then yes, this is my free body diagram, but I'm gonna add a few things to that. These are my points. So what I have on these points, I have these point loads. Okay. I have these point loads. Under these point loads, my cable gets a straight shape in between these point loads, as you can see here, as I explained at the beginning. Then what I have, okay, at the left and right hand side, I have two supports, at the point A and the point B. I have two supports. So if I have a support, why I use actually these supports? Okay, this cable gets all the loads and transfer to the supports, and these supports transfer all the cable loads to the ground or any other main structure. Okay, so we have supports. Let's change the color here, blue, for example. I'm gonna have here support reactions. For example, point B here, HB and vertical B here. This is the angle. Theta B. It's same for the point A. Vertical A, horizontal A. Okay. Angle is, remember, angle is always important for us because it defines the direction of the force. Okay, okay, we can calculate HA, VA, but at the end of the day, the main support reaction, the resultant support reaction is combination of this HA and VA. This HA and VA are the members of the dissolved form of the main support reaction. Okay, we are going to combine it at the end of the day. Okay, this is the free body diagram of the problem. We can see here all the forces, external forces, or all the support reactions. So we have to solve this one. We have some assumptions. Okay, let me write them here. In this problem, all the loads are in vertical direction. Okay. All the loads are in the vertical direction. And second assumption. For example, the vertical distance of any point is known. We know the vertical distance of any point. Okay. The vertical point is known. We know that. and the other assumption here is if we would like to find a tension force any point, that means we know its distance to any support. I will explain this one in while we are doing an example. We have an example here at the moment. No, for the second session, I have an example. Okay, it takes time because if you'd like to find tension force anywhere else, okay, for example, if you like to calculate here tension force in this cable, we have to know the horizontal distance of this point, as you can see here, x1, x2, x3, each point's distance is known, and vertical are also known. We will give all these information that you need to calculate tension force in the question. Okay, this is just to explain what we have. Okay, let's jump to how we are going to calculate these forces. Okay. Now, by the way, question regarding how many support reactions we have in here. As you can see here, we have 2 supports, and for each support, we have 2 support reactions. Totally, we have 4 support reactions to solve. This is interesting for us because if you remember our beams, at the end of the day, we generally have 3 support reactions, and at the end of the day, we have 3 equilibrium equations: total x, total y, and total moment is 0. So 3 unknowns, 3 equations. It's easy to solve. That's okay. There is no problem. But here, what we have 4 unknowns, but 3 equations from the equilibrium. Okay, we need to find one more equation to solve problem. Okay, one more equation. Let me write. Okay. Right here. For the 4th equation, what can I do? I can cut the system from here. Please take a look at this one. Because why? I know that when we look at all these C1, C2, and C3, the only point that I know the vertical distance is this C1, C2. Okay, when I apply this load, my C1 is here, but I don't know this distance. I don't know this one. I don't know this one. Because to write the equilibrium equation, I need distances. Okay, I need distances. But here we have y2. That's why I cut the system from this C2 and take into account the left portion. Okay, let me write it here. By the way, what I have, let me write that point. There are 4 support reactions, right? Yes, we know this one. And then we have total x equals 0, total y equals 0 and total m equals 0 from medium. Okay, we have three equations. We need one more. We need one more. One more equation. Solve problem. Okay. So let me change the color. We know these three. For the fourth one, what I said, we are going to cut the system from C2. Let me draw C2 here. Here I have P1. Here I have P2. Here's C1, P2. And here what I have support reactions. This is point A, H, A, vertical A. That's okay. By the way, this is B1. B1. And okay, I know what I know regarding the C2. I know the vertical distance from the point A. I know this one. That's why I cut the system from C2. Okay, for so for this point C2, I know the vertical distance and also horizontal distance. So I know where this point is. If I know the location of this point under this loading, I can make calculation because at the end of the day, I'm gonna take into account all these distances. For example, let's have a look to C1. Okay, for C1, I know this X1, but I don't know this one. Okay, that's why I cut the system from C2. Okay, this is the logic behind this. If I know both direction, both distance in vertical and horizontal directions, so cut the system from there in cable questions. Okay, so if I know everything at this, regarding the C2, can I write this equation like total M C2 equals 0? Yes, I can write, because what I said at the beginning, this is a cable, this is a bendable material, bendable stuff. So they don't carry any bending moments. So I know this, so I can write this equation. The total, actually, at each point, at every point on this cable, total moment is 0. That's okay. No worries. But since I know only the distances in vertical and horizontal directions for C2, I write this total MC2 equals 0. This is the fourth equation. Why? Let me write again here. Why select this C2? This is only point. Only point vertical distance is vertical are known. Okay. So we cut the system. We write these total MC2. By the way, when we cut the system point C2, okay, at the right-hand side of the point C2, there was a cable here. There was a cable. We cut the system from there. Where is it? We have to consider its effect here because it has a tension. You know, cable carry on the tension. It has a tension. It acts to this point. So we have to draw the tension load here. 1, 2, 3. Let's say T3 here. Okay. What is the direction of this T3? Let me write it here. So in C2, 3, C3 direction. Okay. This T3 goes directly from C2 to C3. Remember, C3 is around here. We don't know. Let me show you. Here, C3 here. T3 is in this direction. Okay, we have this system. For what we can write for the support. I will write something for this part. This is the equation. So what we are going to do later on, we will write here TA. How TA is total support reaction. Tension at the point A, actually, T represents tension. Support reaction at point A. So, okay, when we resolve this TA, we are going to get HA and VA here, these two. That's okay, but I don't need that. I need the total support reaction and its direction. That's okay. If we combine this HA and VA, we can get the TA. How we can combine it? Okay, what do you think? You know how to do it from the subject force in the first and or second week. We talk about the combination of these forces. Let's do it. HA square plus VA square gives you the TA. If you would like to know the direction of the TA, which is delta A, VA over HA, tangent theta is VA over HA. From here, you can get the theta A. It's same for the right-hand side. Right-hand side, EB equals HB square plus VB square. So tangent theta B equals VB over HB. From here, you can get the support reactions and corrections. Now, we know HA, VA. So with this equation, what we did, for example, with this total MC2, what we did, we firstly calculated support reactions. Okay, as you can see, according to this equation, I have this part at the left-hand side. For this point, C2, if I write this equation, total MC2 equals 0, I can calculate HA and VA. Okay. After I calculate HA, VA, I can calculate, total support reaction, which is here. And its angle. It's same for the point B. If I use the other side, yes, I can do it. TB equals HB squared plus VB squared and take square root. That's it. It gives you the total support reaction. So in the first equation, what we did, we calculated the support reaction. After we get the support reaction, yes, we can calculate the other stuff. For example, if I ask you what is the vertical location of C1, let me write it here. After calculation of HA-VA or HB-VB. Okay. A calculation of a vertical distance of any point. For example, here in our, for example, C1. Remember, where is C1? C1 is here. We don't know its location here, as you know. As you know from the question, we don't know, but we can calculate it. Okay, after we load this point, how much it goes down? Where is the latest location with respect to this support? Okay, we can calculate it. So we can write here HA, cut the system from C1. We know HA and VA anymore. We can do it after we calculate, after we get the support reaction. Okay, firstly we get the support reaction with the first step. Now we know VA and HA. So this is C1. Here is P1, and this is the distance x1. Here we have a cable load P2. Now, under this loading, what we are looking for? We are looking for this one, Y1. What is this? From the support A. So to do this, to calculate this, what we are going to do, always there's no moment on the cables. Keep this in your mind. Okay. So we can write total MC1 equals 0. So for this point, if we write total MC1 equals 0, we can get from here, get the Y1 from this equation. So at the end of the day, we are not doing a complicated calculation. We are doing just total moment equals 0. Total moment equals 0 for our selected points. In the first stage, we selected C2. Why we select C2? Because we know the vertical distance of this C2 from the support points. So we can calculate, make any calculation for that point. What we did, we write the total moment for that point equals 0, then calculated the support reactions. Okay, we know the support reaction, we got it. Now we're using that support reaction for C1, for example. What is the vertical distance from any support of C1? Yes, that means what is Y1 in this question? We know the HAVA and we cut the system from the point C1, write the equation total MC1 equals 0. So if you do this, you can get Y1 from here. Okay, Y1. And any other things, let me see. What we can do for, okay, we calculate the Y1. From here, for example, this point is C1, and I have an external load C1. In the cable directions, we have tension forces. Remember how we represent a tension on a point. If a force goes out from the point, that's the tension. Goes in, if goes in, it's compression. So I'd like to draw the tension force here. And other one is what I know here. Here is the angle, theta 1, theta 2. Okay, after we calculate the theta 1 and theta 2, how we can calculate, by the way, these theta angles? For this point, for example, for this point, V1, for this point, we know X1 and Y1. So that means I know this angle. I know this angle. It's same for the C2. So that means I know this angle, theta 1, and here theta 2. If I know the thetas, these angles, I can calculate the tension forces. Tension forces. What can I do to calculate these tension forces, T1 and T3? At the end of the day, we don't have any moment at this point. To calculate T1 or T2, I don't need any moment equation. I can write directly total X 0, total Y 0. Tension forces on the cables. Okay, what we did. I'd like to sum up and then go to the next stage. So at the end of the day, these type of problems, that means cables under the point load, we have four support reactions, and three equilibrium equations. That means we need one more equation. So where we can find it? We are gonna take a look at the system. Let's go back to the main page, page 4. We are gonna take a look at the system, as you can see here. Look at the load points. We only know the both distances from supports for C2. So as you can see, we don't know the vertical distance for C1 and C3. That's why I cut the system, take into account this C2, cut the system from C2, because we know that distance. And write the total moment equals 0 for that point. Okay. If you do that, where is it? Here. If you do that here, you can get the support reaction. Here, in this example, we'll just calculated the HA and VA. And then if you combine it, you're gonna get TA. So TA, support reaction, equals the tension load of the latest or last cable portion here. If you write the equation, you can get it. Calculate the TA. After that, we know the TA. If you like to calculate the forces of this point C1, because we have two forces from here and here, left and right hand side. We need to calculate its vertical distance. To do it, cut the system from C1 and write the total MC1 equals 0. Then you can get the vertical distance. After that, after you get the vertical distance, calculate the angle. How we can calculate the tangent theta 1, for example, for this one, equals y1 over x1. Get the angle. If you have the angle, so you can write the equilibrium equation for each loading point. There's no moment, we know that. That's why we don't use any moment equation here. Total x and total y equals 0. You can write total x and total y for this point. If you write these equations, you can get T1 and T2. This is the cable under point load. This looks like really complicated for you. I know. But regardless of the calculation, I always try to give you a logic why we are doing this. The other stuff is just calculation. Use your calculator, do it. But if you understand why we are doing these 4 steps, why we are cutting the system from here or here, to solve the problem, there is no problem. But you have to do a few practice. Now we have just completed the loads under the point loads. Let's do the points under the distributed loads. I'd like to complete it first session, all the subject and solve problems. Okay, cables. Under distributed. Yes. Load effects. Okay. Yes. Let me draw the. I will summarize the subject. I'm not going to do everything here for you. Okay. Let me draw a table here. From here. These points are the support. Okay. This is a symmetrical table. By the way, remember the main differences is here. If you apply distributed load on these tables, they still have a curved shape. Remember the point load effect. After the point load, they get a straight shape, you know. But here it still have a curved shape. At this point is the middle point. Let me draw here. And this is X, this is Y, this is Y. What is the loading on this member? Loading is like we apply loading, like the suspension bridge example. This is the main cable. From the bottom, a uniform distributed load acts on the cable here. Acts on the cable here. This is the Q. And then let me go to here. Horizontal B, vertical B, horizontal A, vertical A, and this is point A. And here we have point C. And what is the span in between 2 points, 2 support points? Span in between 2 support points is L. Okay. Now, one more thing we need. This is the support, you know, for example, point B, and the point C is the lowest point of the cable under this loading, right? So if calculate this distance, this is F. Okay. This is F. Here, F, L is span, F is sagging. Sagging means in Turkish sarkma miktarı. F is sagging. Okay, we have this system under uniform distributed load. Okay, uniform distributed load. Now, if we cut the system, if we split the system 2 pieces, if we cut the system from point C and take into account the right hand side, let me draw that part here. This one. No. Wait. Like this. And let me write all the forces again here. H, B, B, B. What I have here. again, this is load, half of the load, okay, half of the number. So this is 2, that's okay. Here is the point C, here is the point C, and what I have at this point C, I have a tension load, which is represent the other half of the table, and then I have having F here. F here. By the way, here is, remember, the total span in between point A and B is L. Here is L over 2. L over 2, because we cut the system from the midpoint. Now we are going to write the equations, equilibrium equations. Total x. By the way, if I cut the system or from right hand side or left hand side, no worries, regardless of the right or left, I'm going to write this equation, okay? Because if I choose the left hand side, the equation is again same, because it's completely symmetrical system. Here, total x. Here, if we take a look at the total x, by the way, here is T0, okay, this is T0. Total x in this system. What we have HB in the horizontal direction we have, and T0, right? They are in the opposite direction. That means HB equals T0. HB equals T0. For the symmetrical side, for the other side, HA is same, equals HB equals T0. Okay. Total Y equals 0. For this system, for the vertical A, vertical B equals 0. For the system, vertical A plus vertical B minus 2 times L equals 0. Here, vertical A goes up, vertical B goes up, the Q goes down. They are all in the vertical direction. Vertical A plus vertical B minus QL equals 0. And then total MA, equals 0. We know for cables, each point we have 0 moments. So for MA, let's do it for MA. We have this vertical load. 2 times L is the combined version of this thing from this 2. 2 times L. This is the load. Times L over 2. L over 2. This is the moment. Okay. Minus. This turns the system in this direction. So vertical B turns the system in the negative direction. That's why I use vertical B times L equals 0. So vertical B here equals 2L over 2. So vertical A equals this one. And we cut the system from point C here, as you can see. Let's write the total MC. HB, HB times F. You know, I'm going to take moments around point C. HB is a lateral load, but it has a vertical distance, which is F. So I have to consider it. Yes. HB times F minus QL over 2. 2L over 2. Here is this load is QL over 2 times L over 4. The distance to this point. Oh, sorry, this point is L over 4. L over 4. Write it here. Times L over 4 equals 0. Here we get HB equals 2L squared HA and equals T0. This is an important equation you have to know. You can see here T0 at the bottom. So there is no change in the horizontal loads in the system. So T0 is minimum tension on the cable. Minimum tension in the cable. So you have to know this equation, QL square over 8F. 8F gives you the T0. Also under this uniform distributed load, it equals to HB and HA. We have to know this. We have to know this. Okay, T0 is important. There is one more thing before the break. The length of the cable. I'm not gonna write. There is a explanation, mathematical explanation of this cable length, but it takes time. It includes integral, some differential equations. I guess we don't need that, so we don't have any time to do that at the moment. I'm gonna write the formulation here, and then while we are doing examples, we will use the length of cable. The equation is X times the cable length times HP. This equation gives you the half cable length, SP. Okay. Please, we will see how we use this YB, XP. What are they in the examples? But keep in your mind, SB is the half of the total cable. Okay, cable length is 2 times XP. You have to know this equation. Okay, we will see this in detail in the questions with the numbers here. I can't explain more at the moment. Keep this in your mind. You have to know this equation. Let's have a break, half an hour. Now it's 10:15. We are going to be here at 10:30. 45. Okay, guys. See you. Okay, let's get started to examples. As I said to you, this subject is really, really easy. I think you can do, I know you can do this. I will show you a few examples and solutions. Let's get started. Okay. Okay. That means we have a distributed growth on the table. F, F. Yes, this is the question. Sketch actually, like the question in terms of given values. L, determine by the maximum force Tmax angle of Tmax and the length of the rope and the of the rope. Okay, here we have a cable with uniform distributed load, L, F, Q, all they are given in the question. Let me write them to the sketch. Okay, to see what are they. Okay, L, well, L, yes, here it's 100 meters. And F is 10 meters. All they are coming from the question. Q is 100 kilogram meter. Okay, what the question asked us, what is Tmax? What is delta Tmax angle? And what is the cable length? Okay, according to this question, we are asking here 3 questions. So, basically, what we are going to do. By the way, I would like to explain this. Tmax, the maximum cable force is always occurs at the highest point of the cable. Okay, when we have a look at this cable, you can see A and B they're at the same level, and the cable sags down. So what does it mean? The highest point on this cable is point A and also point B. They are at the same level. So we have to know that the maximum tension load always occurs at the highest point. Okay, if I change the question, okay, if I ask you cable like this, one support is here, this is not asymmetrical. cable. This is A, this is B. If I ask you to calculate the maximum cable load, so you have to calculate the cable load at this point, because this is the highest point of the cable. You know, this is at the lower point than the point B. So this part, this portion gives us the maximum tension load. Here we have equal level for point A and B, so the maximum load occurs at one of these points. Okay. So the support reaction actually is the maximum tension load here. Tmax, calculate Tmax. By the way, let me write here what we have. We have vertical A, horizontal A, horizontal B, vertical B, right? Okay, so we know that the maximum force occurs at the support. So this support loading is equals to maximum tension load on the cable. Okay, so if we calculate the support reaction, we get the maximum tension load. Here you can select so left and right, one of them, left or right sides. But by the way, before that, we have to calculate vertical A and vertical B. How can we do that? You can remember this. Here we have a Q, which is uniform distributed load. This is a symmetrical system. Basically, half of this Q goes to right and the half goes to left. Vertical A equals vertical B. The support reaction Q, by the way, what we do for the remember how we convert this point load. Q times L, we calculate the area. 100 kilogram times L is 100. Okay. So if you calculate the support reaction, half goes left, half goes right. So times L over to here. 5,000 kilograms. Now we know 5,000 here. Okay. 5,000. HB, horizontal loading. So remember the horizontal load on the cable P0, which is the minimum load also at this point. We have this T here, and at each point we have same T0 actually. At the bottom point, by the way, let me explain this part again. Here we have a cable. We are now at this point. We have at this point T0. For example, if I like to calculate, this is the most bottom point. So we have only horizontal loading on the cable, which is the minimum tension load. If we go a little bit right or left, it's the same. Okay, we have this T0, it's constant all the way up to the support, but at the same time we have a vertical component here. So here the tension force is higher than this bottom point. If we go a little bit up, okay, here we T0, that's the way we have one, for example, one vertical to a different vertical load. So this load will be different, tension load. This is the tension load on the cable. But at the bottom, there is no vertical component. That's why there is only T0. T0 means here for the cable, it's the minimum tension load on the cable in the horizontal direction. Yes, what we understand here, T0 always is T0 at each point of the cable. We have T0, T0, T0 everywhere, at support also. So at support, horizontal support reaction equals T0. Basically, T0 is everywhere. Okay. At the most bottom point, there is only T0. After and all other parts, there is T0. Also, there is one vertical component. One vertical component. Tension load is combination of these T0 and the vertical components. Okay. Now, we have vertical A and vertical B. What about the HA or HB? Here, HA. HA equals HB here. What was the T0 equation? To 8F. 8F. So here T0 is Q is 8 times F. What is F? 10 equals. And here, the total T0 is 12,500. Now what we have? What does this mean? Now T0 equals HB. So this is vertical B. Vertical B is 500. Look. So T max is combination of these forces. Combination of these forces. Okay, let me write T max here. I guess you can write it here. T max equals 5,000 square plus square, and from here T max is, let me see, if you do this, you're gonna get this is the T max. Okay, theta max is this T max. Here we go. Theta T max is arc tangent over here 5,000 or this. The angle here is 21.8 degrees. This is the theta T max. Okay, we did this one and this one. Now, cable length. Okay. What was our equation? What was our equation? I don't want to change the page actually, so that's why I'm gonna clear this part. I'm gonna write here because I'm gonna use the sketch. open a box here. Okay. Line of cable. Okay, line of cable. Here, it is like SB. Remember, half of the total S. Total S is here. Cable length. XB. This one. This is the equation. This is the equation. Let's write the SB equals S over 2 XB. Here, the total length is 100, XB is 50 times. I'm going to explain it for that first equation. YB so S is okay. This is the equation. Let me explain. Firstly, I just wrote the equation and the calculations. Let me explain the case. Okay, we have to know this equation SP equals XP times 1 plus 2 or 3 times YB over XP squared. When we look at this table, here XB is this part. Okay. XB is here and YB is here. Totally YB is S. XB is half of this span. Okay. Here XB is half of span. YB here. F. Sagging. Remember, Sakma. So if we put XB and YB, the equation given here, we are going to get 51. 51 is half length of the cable. Remember, S over 2. We are looking for S. Always, after we get this SP, we get double of it. Okay. Total length is 102. Remember, span is 100 meters. If you keep this as it is 51, imagine that this 51 is less than the span. It doesn't work. You cannot connect point A to B. So this S should be greater than the L span. Basically, this is a logic to check what you are doing. I think, yes, what we did in the question, we calculated Tmax, beta max, and cable length. Okay, let me solve another question. We have many questions like that. Where is it? Yes. One more question. Here again, we have 2 points. We have 2 corners like this. And we connect these 2 corners table. A and B, A and span is 30 meters, and we have 40 kilograms per meter from distributed load. Meter. Okay, A. Determine the sag F of the simple cable of the simple cable system given. Given in the figure. If the maximum cable force Emax is equal to 121 kilo. Okay, this is the question A. This is B. Calculate the total cable band required and such a distance. Okay. Okay, these are the final exam questions we asked a few years ago. The previous question was like that. This is also a question we asked. Here, what we have. Okay, we have a uniform distributed load on the cable. We have F sagging. What the first question asks? Okay, there's 40 kilogram distributed load. Calculate the F. Calculate the F if the T max is this one. T max. Okay. Firstly, if the question gives us T max, what is T max for us? Where it occurs? Remember, T max always occurs at the highest top point of the cable. So we have two top points, point A and point B. Okay, let's say we are dealing with point B. The T max will occur also at this point and this point. T max is this. T max. Okay, this is the T max. So, okay, we have T max, but remember, we have two components to get T max. Vertical B, horizontal B. So we know this horizontal B is asking for F. First question asking for F. Remember, what was T0? T0, Q, L square, F. So T0 equals, remember, T0 was the tension load at the bottom. So it was constant during the cable, all the cable point. So it's equal to the HB, equals HB. Okay. if I calculate HB, I can get F from this question. That's okay. It's easy. I have T max here. T max. This one equals vertical B square plus HB square and square root. That's this one. Okay. What I have, vertical B is, remember, Q times L over 2. Vertical B. Q is 40 times 30 over 2. Okay. This is 600 kilograms. So I have this equation. I can put this here. Equals HB square. I can get HB from here. When we write this equation, you can get HB. HB is here. What? Let me see the result. What is HB? I guess it's 400, 100 kilograms. Also, this HB equals T0. T0. So here, I'm going to write the equation here again. T0 equals HB 400 kilograms. So 400 here equals Q. What is Q? 40 times per square over 8 times F. 8 times F. So from here, they can get F. F is 11.25 meters. Okay, this is question A. Let's do question B. Question B is asking about the total length of the cable. Yes, SB, remember, S over 2 equals, we have to know this equation. We have to know this equation. XB times this is the equation. Here, SB is SB. The total span was 30 meters. So this is 15. Remember, half of the span, XB plus 1 plus 2, 3, and YB. YB is F. Here just calculate it, and 15 square, this one. This is the SB here is this one, and remember S is double SB, so it's 41.25 meters. This question B. Any questions so far? Ask different questions. Let's see. Okay, we have one more question here. It's almost same. Logic is same. You have to know in these questions. You have to know what is T0. What does it mean? Okay. You may know the equation. It's easy, QL square over 8F. It's easy, but you need to understand what it is, where you can use it. Okay. If you know these equations, that doesn't mean you understand the subject. You can know all these equations, but you can't use them. That's why please try to understand what is T0 exactly on a cable. Okay, T0 is the minimum tension load at the most bottom point of the cable, because there is no vertical component for that point. If we go above the support, we are going to see the horizontal component, which is T0, is always constant over there. And we add extra vertical components. So the tension force on the cable is combination of these two horizontal and vertical forces. But at the bottom, we have only horizontal force, which is T0. That's why it is the minimum tension load on the cable. Okay, let's do one more example. Again. Q, again, uniform distributed load. Uniform distributed load. Here we have F. Here we have L. Okay. Here A. Here B. Okay. The first question, A. L is 46 meters. F is 6 meters. And Q is 350 kilogram meter. Question is Emax. QA, theta A, theta B angles, and cable length. Okay, here, as you can see, the cable system and all the data is given in the question. What we are going to do, we have to, for A, for this question, we have to calculate the vertical and horizontal components for support. You know, the maximum tension force occurs at the support point. H, A, V, A, V, B, H, B. Okay. Now we know the Q here, so we can calculate the vertical A or vertical B. Vertical A equals vertical B. Okay. So here QL over Q. Q, what is Q here in the question? 350 times L. L is in the question 46 meters over 2. Result is 8,050 kilograms. Okay. Okay. So we know vertical one. So remember that the horizontal, the minimum tension load is minimum, and the horizontal component of the cable force. So HB and HA equals to the T0 HA HB 8F. Q is here, Q L A times 6. Okay. Here you can see we have vertically and horizontal A. If you combine them, you can get the maximum load. Tmax is combinations like that equals yes, this is Tmax. This is Tmax. We'll just calculate Tmax. Theta A, theta B. Here with each other, theta B angles. The arctangent of the vertical over horizontal. This is vertical over. This is the horizontal one. Here, if you do this with the calculator, you're going to see theta A equals theta B equals 27.55 degrees. This is the yes, this is the angle. The last one is cable length. Cable length. That's okay. SB. You know the equation now. SB equals S over 2 times XB half of the span, which is 23 times okay, y 6 over 23 square. Okay, if you do this equation, you're going to see this one. S is double. Okay, this is the question A. And by the way, let me write the question B here and C. B is if L is 50, Tmax yes, and Q rounded meter. What is S? Table. This is question B. And I'm going to solve one more. Question C. Here is if S 60 meters, L okay, L is this, right? L is 10. Tmax for the 6 ton. So what is Q? These are the all versions of the questions you can come across. Okay, we have just solved A here. This is A. Let me solve B to the next page. B. L is 50 meters. Tmax is on. Q is 400 kilogram meter, and S here. Okay, Tmax. Tmax is the combination of the horizontal force and the vertical force. Let's write the Tmax. What is the vertical component? If I have this one, remember here I have, for example, HV here, Tmax is here, Tmax is here. Let's go from here, vertical B here is Q times 50 over 2. Okay. Over 2. So you don't have a compared to write. Anyway. Result. This, by the way, just a second. Here, this is ton. Okay, this is kilogram. We need to convert this to ton. Okay, let me change here. Now this is the vertical B. Now let's write Tmax equation. Tmax equation. Tmax is the vertical component square plus horizontal component. Horizontal component is T0. Remember, HP is T0. T0. Q is times F. That's okay. Tmax. So what is this part? This is vertical B. This is horizontal B. So Tmax actually is given in the question, which is 50. Let me change here. Tmax. So in this equation, how many unknowns we have? How many unknowns? One. There is only one unknown here. This guy. So from here, F is 2.11 meters. If you know S, you can calculate S. So S equals half of 25. 25. $25 square, this guy, and the SV. So S is double of SV. Okay, this is the S. Question B, and let's do question C. What is it? Here you can see S is 60 meters, L is 58 meters, Tmax is given here 46 tons. What is Q? Okay, let's do C. Let's do C. S, yes. Meter. L is Tmax is, what is Q? Q is, what is the magnitude of uniform distributed load? Okay. magnitude of uniform distributed load. So we know S. We know S. Remember, S over 2 equals XB plus YB over XB. Okay. We know the total span. So if we know the total span, we know XB. The only thing that we don't know here in the equation is YB. What is YB? YB is the sag, which is F. This equation gives us the F. Okay, let me write it here. It's over 2 SB. It's half of the square. 29 here. YB. I don't know. Or we can write here F instead of YB. F, because you know F equals YB or YB equals F, whatever. Okay, from here, there's only one unknown. You can solve it with your calculator easily. F is here 66 meters. We know F, T max. Okay, what is T max? Remember, T max is change color. T max here is 2L over 2 square. Oh. This one. This is T max. What is this? This is the vertical component. This is horizontal. Also T0 gives us T max. So here we have all unknowns except Q. We are just looking for Q. Actually, in this question, as you can see, T max here for the 6 equals Q. Q is Q. 2 times L over 2 square plus 2 times L. L is 8 over 8. F is 6.6. Okay. Okay, you're going to solve this equation. There's only one unknown, Q. It's easy. If you make arrangements on this equation, you can solve this Q easily. Q is here. Calculated 0.66 ton per meter. Then a question type that I didn't solve. I'm just checking that. Actually, I solved each type of question regarding cables. Is there any question? Is there any comments? Anything else? You all will understand this one. You're going to ask cable question in a final exam. This is really easy. Please catch this question. Okay, this is easy. It's really easy. Oh, yes. have this one. Okay. Yes, I just calculated all type of the question. Okay, ladies and gentlemen, if you don't have any question or comments, I'd like to close the session today. Any question? Anything else? No. I would like to remind that please, if you want to get a makeup exam, if you didn't attend our midterm exam, please email to me with your official documents, such as doctor report or any kind of official document, till tomorrow 10 p.m. Okay, I'm going to send you an announcement from the system. You're going to get an email. So we're going to organize a makeup exam for you. This is not for the students who has joined the midterm exam and they would like to get higher values. Okay, this is not for you. This is only the students who didn't attend the exam for a reasonable excuse. Okay, ladies and gentlemen, thank you so much for today. I'm going to send you the reminder for the makeup exam. Please let me know if you need to any exam. Take care of yourself. By the way, we don't have class next week, you know, New Year day. From now on, I would like to wish you a happy and healthy New Year. I hope the New Year will be better than the previous ones. Take care of yourselves. Bye bye.
Thank you, hocam.